Alright, some very good questions here. 18, 19 and 20. For a wheel that is rolling without slipping, okay, rolling without slipping, what is the relationship between the wheel's rotational speed and the speed v of its center of mass? Okay, well, this is the relationship. The velocity of the center of mass. So here is the object, and remember, it rolls down, but there's no slipping here. And we identify the center of mass of this object. Then the velocity of the center of mass equals the radius of that wheel, okay, multiplied by its rotational velocity, okay, the rotational speed. So that's the answer there. It's very straightforward, but the important thing is to not confuse it with this guy that we've seen before. Vt equals r omega. They look identical. V is r omega, V is r omega. But there's an important difference. That this equation, which is from equation 1110, okay, this is the velocity of any point. So say now this object is rotating about that point. This velocity refers to the tangential velocity. So if we measure, say there's my r, and that will be my tangential velocity of that point, right, as this is rotating about. Whereas this is the velocity of the center of mass. So make sure that you identify what the difference is between these two equations. Okay? Second one, 19, if two gears are in contact, okay, with their teeth meshing. So, I don't know. Okay, just use your imagination. And there's another gear there. Okay, two gears are meshing. Okay, they're meshing. What do they have in common? If two gears are in contact with their teeth meshing, what do they have in common? Rotational speed, right? Rotational speed, omega. Tangential speed, Vt, right? Vt, tangential speed Vt, or some other quantity. Well, what do you think is the answer? So they're both rotating like this and they come into contact. Well, they definitely have the same tangential speed. Okay? Because at this point, when they're in contact, they have exactly the same speed. So now they're rotating this way. So at that point they have the identical Vt. Okay? Definitely the same tangential speed. Now the second is rotational speed will only be the same. When? When will the rotational speed of these two guys be the same? When their radii are the same. Okay? So if you've got a small gear and a large gear, their VTs will be the same, but their rotational speeds will be a lot different. Okay? Because their radii are different. Okay? But if they are the same size, then their VTs will be the same and their rotational speeds will be the same. Okay. Now 20 is very important as well. What is the shape factor for a rolling object and what does it measure? What is the shape factor? C. What is the shape factor? Okay. So here we have. So go look at equation section 12. No, I don't remember what 1220. What was 1220? Oh, sorry, brain freeze. This is the question we're looking at. But go and look at this equation and go and read up this in this section. Okay. Sorry, I prepare notes and then I have to remember what I've written down. So, what is the shape factor? So if you've got an object that is rolling without slipping, right? It's rolling down here and rolling, without, there's no slip. Then the acceleration of the center of mass is given by this equation. Okay, it's given by g sine theta divided by 1 plus I over mr squared. Okay, and this I over mr squared is c. So it is your rotational inertia divided by mr squared. And so the important thing to see here is that a couple of things. This value c tells us by how much the acceleration is going to be reduced. Okay, what do we mean by that? I think we've seen this before. A equals g sine theta. Where have you noticed that before? Well, that is if you've got an object that is sliding down an incline, right? You've got your angle theta, okay? And the acceleration of that object is equal to g sine theta. So we've seen this before. But now, if we've got rolling without slipping, then we take that value that we've seen before and we divide it by 1 plus the shape factor. Okay? And the important thing is that it becomes independent. I divided by mr squared becomes independent of the inertia and the radius, and it is only dependent on the shape of the object. It is only dependent on the shape. Okay? So, it says here, for all objects of a given shape, the time interval to roll down a ramp is thus the same. So, if you've got a small solid cylinder or a large solid cylinder, okay, remember C is independent of the inertia and it's independent of the radius. The only thing that's important is the shape, right? These two have the same shape. Or if you've got a hollow cylinder like that, or a large hollow cylinder, then the shapes are the same, which means they will have the same acceleration. So we take this g sine theta and we divide it by 1 plus that shape factor. So, for example, a thin-walled cylinder or hoop, its shape factor I over mr squared is 1. For a solid cylinder, the shape factor is a half. Hollow core, it's this guy. Right, these are the shape factors. So you're going to have, so for example this, if you've got a solid sphere rolling down a hill, then it's g sine theta, which again refers to just an object that is sliding down. But now, if it's rolling without slipping, then you have to add 1 plus 2 over 5. So you are reducing the acceleration by 1 plus c, right? Or 1 plus 2 over 3, or 1 plus a half, or 1 plus 1. Okay? Alright, so hopefully that helps. Let's see, is there anything else here? Please go read this. Read this section in the textbook. Make sure you understand it. Cheers.